So now, for our Nightlight circuit here, we are dealing with a relatively fair amount of current. I'll move the power supply over there. I have it set to a maximum of 300 milliamps of current, but there you can see we got more than 200 milliamps of current. So I would not use a 2N3906 to switch this because it has a maximum of 200 milliamps of current that it can switch, and we exceeded that. And you shouldn't push things to their limit anyways. I try to stay about halfway. So the 2N2907 can switch about 600 milliamps of current maximum. So I try to keep it below 300. But in case, it's also a PNP bipolar junction transistor, just like the 2N3906. This can be thought of as the PNP version of the 2N2222, which is an NPN transistor. They got basically the same capabilities but opposite polarities right there. So we need a little bit of emitter to base current right there in order to turn the transistor on. Now, this is a somewhat significant load. Definitely is for this particular transistor. So instead of a 10K resistor, we got a 1000 ohm resistor right there. And so it's going to let about 10 times as much current. And whatever we're going to switch, we want at least like 1% of that amount of current going from emitter to base to make sure that the transistor turns on fully. Not going to dwell on that too much. That's basic transistor switch stuff. But in any case, we have a comparator here, LM393, and there is the pin layout. And again, it is only intended to sink 16 milliamps of current. So when we were lighting an LED, it was possible to just sink the current through the output there, but we would be, pushing it towards its limits as well. As I said before, I try not to do that. So this pull-up resistor, just to make sure we got 5 volts at this point when the output's high, because it doesn't output positive voltage from the power supply like that to the output. It only connects to ground. It's a transistor like this. It's called an open collector, the output, and other integrated circuits have that same output. When it says open collector, that's what it means. There's a transistor that switches to ground when the output is low, and turns off when the output's high. And so it may pick up stray signals and stuff. So it's not a bad idea probably to have a pull-up resistor, but I think you'll actually probably be just fine without it, especially in this case right here. So we have that bright LED. It's a 5 volt 1 watt LED, so we can still switch it with 5 volts. And when I bought it, it did not have wire attached. It has a couple of little pads there, and I filled up the pads with solder, and so it holds the wires pretty good. But you just put 5 volts across it. It already has a resistor built on there, and this is a heat sink right there. So that helps dissipate heat. That's why that little resistor can dissipate so much heat, because it's attached to a heat sink. When you add metal to components, it helps them dissipate heat greatly right there. So in any case, we come back, and it's an LED right there. You can just see the LED. Pretty straightforward, and it tells you plus and minus. I know it's kind of hard to read on there before you wire it. I think it says B plus on the positive side and then B minus on the negative side. Let's get that in there. Try to avoid a short circuit. There we go. Alright, so yeah, we got to get it dark enough. That's because it is a comparator. We should probably get to that, because that's the main part of the circuit. Although, I just wanted to warn you, this is a power-hungry load for basic electronics. In my opinion, not super power-hungry, but for simple circuits, it is. So, this, as I said before, does not output the positive supply voltage, doesn't source current, it only sinks current. When the output's low, it will go to ground, and so that's why we've got to pull up. We need a resistor, otherwise we would have a direct connection, positive supply to ground through the output. There should be short circuit protection though, but in any case, we got the 10K resistor there, so that we can get 5 volts when the output's high, and then it leaks a little bit of current, but otherwise the output goes low and connects to ground. We will move this up. So the symbol has the plus below the minus. That's the same way on the physical component. Always pay close attention to where plus and minus are. If it's easier to draw it with the plus on top than minus for some reason, people will do that. So always pay attention to that. I'm going to try to always remember to remind you of that when I'm making this, because it's very important. Physical component, it doesn't change. positive supply top right, negative supply or ground to the bottom left. And so there you can see right there, pretty straightforward. We wired it. I'm not going to do a step-by-step build. So we got this, I shorted something. Or no, I covered that, luckily. So we got the plus input right there, the non-inverting 10K resistor to ground, and then light dependent resistor here. So light dependent resistor, its resistance changes depending on the amount of light on it. I can cover it with my finger to make it darker, or turn the lamp down to make it darker. When it gets dark, its resistance goes up. So let's see why that matters here. Again, this is a non-inverting comparator. We got our reference voltage, half of the supply voltage, to the inverting input. Our signal, the light dependent resistor basically, and then in combination with that 10K resistor, the light dependent resistor and that resistor, the voltage divider, is coming to the non-inverting. Output wants to be more like the non-inverting when it comes to a high-low voltage. So when we got a higher voltage, because light is falling on here, it's making a better connection, less resistance to the positive supply. We're above 2.5 volts right now, and therefore it's a higher voltage that doesn't output high. Remember, the pull-up resistor is making sure the transistor turns off. Although without current flow, the transistor is going to be off anyways. So probably don't need it, but usually you'll see this in, doesn't usually hurt anything. You usually see it in drawings. Now, if we get it darker, so let's look at that again. We got it darker, and I definitely messed something up right there. Let's wiggle all these. Power supply is on, and okay, let's see if I think yeah, oops, that was really bad. I pushed way too hard. So now we're back. I had to straighten the legs a little bit. Didn't take too long, but I figured you probably don't want to watch that. So in case, we get it darker, and what that's doing is we're getting more resistance with the light dependent resistor as it gets darker. So more resistance makes it so that it's harder to connect to the positive supply right there, ultimately making the voltage lower right there. So the resistance isn't changing here, but we get less than what we have up there. We get it darker, it goes above 10K resistance. That's the main thing. This is 10K resistance, which is lower, and then therefore we got a lower voltage than our reference voltage, and the output goes low. Hopefully that makes sense. Basic voltage divider stuff. But we have an adjustable resistance on the high side based on the light level. And remember, the PNP bipolar junction transistor turns on when the output's low. So usually, or I'm not using a red LED, I'm sick in the last video, the light here will turn on when the output's low instead of high. Some circuits you might want the LED to turn on when the output's high. I think that's more common, but in this case I have it wired so it turns on when the output is low. So you have to be aware that is an option. You always got to pay close attention to every part of the circuit. Never make assumptions, especially with what transistor is being used. A lot of transistors are higher wattage transistors, and that may be the minimum wattage you want to use for a particular circuit. So always pay close attention to the transistor. The triangle symbol could be either op amp or comparator. This pull-up resistor gives you a good indication it's a comparator because they tend to have open collector or similar outputs. Again, that's the transistor. So mention that. We will, oh good, I did write a note, so I didn't look over this whole thing carefully. So yeah, use at least 600 milliamp transistor right there, which the 2N3907 is. So yeah, we come back, and there is our two 10K resistors again. Doesn't matter which direction you put them. So technically this one's backwards if you're reading the color code, but resistance wise doesn't matter. But they're both coming to that second pin down, which is the inverting input. Our output is on top, and we got a 10K resistor also coming to the positive supply right there. So as long as they're connecting to the same spot, this +5 is all the same spot. So if you trace the board carefully, you will see that there's a jumper up there, bringing that positive rail to that positive rail. So all of these spots are a, oops, not this one down here. All of these spots are the same connection on the board, or that is that one. It's for that, it's a little too close to that line. All of these +5 spots right there are a direct connection on the board. So you can either put them to the supply rail, you know, the one where I have the red alligator clip, or the one across there because I got a jumper, doesn't matter, it's all one connection, to the positive input of the comparator here. That's all one connection. So those three, doesn't matter if we plug these two components there or over there, doesn't matter at all. So you may need like small capacitors sometimes if you got long paths and stuff. That stuff is flowing, because there is still a little bit of resistance, but practically none. So we're fine here. Be aware of that. But in any case, we can put all those positives in the same spot, and same with all the negatives. We could plug them all into the same row if that were possible. You know, it's a little cluttered here, but just be aware that this is all a direct connection. There is just a speck of resistance, but it's practically none. For this circuit, it's good enough to just say there's no resistance. So, yeah, I really covered about everything. Again, we're switching kind of a high amount of current. It's a 1 watt LED, and you just use 5 volts. It doesn't convert voltage at all. It uses that voltage directly and sets the current from there. So the LED is going to drop some voltage. The rest is going to go across the resistor. I can't remember the exact resistance. It's written on there. But in any case, you just put 5 volts across it. The wires weren't already on there, though. I had to solder them. And so 1 watt is 200 milliamps of current. And when we looked at it on the on here, that wasn't all current from the light. We can look at how much of the current is the light versus the rest by just removing the light. Pluck the light, and okay, only like 5 milliamps of current was from the rest of the circuitry right there. So it is almost all. You can just say it's basically whatever current you see there is basically what the LED does. It's like 225 milliamps, which is the same as 0.25 amps instead of 0.23 amps, but again, it's basically the same amount there. Very little difference. You don't need to get that nitpicky with these basic circuits. So, in any case, yeah, that's about it. Hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.